previous lesson, we considered a method to proceed from describing quantum physical subsystems, which are parts of the composite physical system, to describe the entire system. In particular, we have shown that how the basic vectors of states of a composite physical system can be expressed in terms of the basis vector of states of each part of it. Similarly, we also expressed operators that act on the state vector of the composite system through operators that act on each part of it. However, it is often necessary to reverse this procedure. It is necessary to go from the description of the whole subsystem, for the whole system, to the description of some part of it, that is, virtually remove from consideration all other parts of the composite system. Such a transition can be accomplished by averaging the density matrix of the entire system over all possible states of all its parts, except the one we want to consider. As a result of such a transition, instead of density matrix of the entire system, we obtain the so-called reduced density matrix, which will describe the quantum mechanical state of its parts. Let's consider the procedure of such averaging on the example of a physical system consisting of two parts, that is, subsystem A is subsystem B. The rho AB is the density matrix of the entire system. Then, if we want to know the average of the observable LA associated only with the system A, we must take the trace of the product of the operator LA corresponding to this observable and reduce density matrix rho A for system A, which is obtained from the density matrix rho AB by taking a partial trace all basic states of subsystem B. On the slide that you see now, it's shown how to obtain the reduced density matrix rho A from the density matrix of entire rho AB system, taking a partial trace over all the basic states of the subsystem B. In addition, on the same slide, for comparison, we showed how to get the reduced matrix rho B if we take a partial trace of all basic states of subsystem A from the density matrix of the entire system rho AB. In these definitions, the set of M vector psi I is an orthogonal basis for a system B, and the set of N vectors zeta I is a basis for a system A. Note that this basis can be chosen arbitrarily. In addition, with the help of EA, we denoted the identity matrix of the dimension n by n for system A, and with the help of EB, we denoted the identity matrix of dimension m on m for system B. Let us consider, for example, the case when system A and B are two qubits. Let's consider the composite physical system, which consists of two subsystems, A and B. And let the matrix of the whole system rho AB have the form of 1 over 2, 1, 0, 0, 1, string of zeros, another string of zeros, and here we get 0, 0, 0, 1. Now, and we assume that two vectors, 1, 0, and 0, 1, is the basis of the subsystem B. Now, our goal is to obtain the explicit form of a reduced density matrix rho A. Now, the rho A, by the definition, equals to partial trace over the subsystem B of entire density matrix rho AB. So by the definition, it's 1/2 multiplied by tensor product of identity matrix and the first basis vector of B, 1, 0. Here we get rho AB and another tensor product of identity matrix on the first basis vector of subsystem B, plus the same expression just for the second basis vector of B, 1/2 identity matrix multiplied by the vector 0, 1 multiplied by density matrix rho AB, and again identity matrix and the tensor product of identity matrix and the second basic vector of subsystem B, 0, 1. So there are two terms in this expression, so let's denote this term as the first term and this as the second, and consider them separately. The first term is equals to 1, 0, 0, 0, 0, 0, 1, 0. It's the tensor product of the identity matrix on the first basis vector on the density matrix rho AB, and on the tensor product on the right and so through the definition of matrix rho AB we can obtain that this is 2 times 2 matrix of 1, 0, 0, 0. Considering the second term in the same way, obtain that the second term equals the matrix 2 times 2, 0, 0, 0, 1. So the reduced density matrix rho A thus equals to 1/2 multiplied by identity matrix, or 1/2 multiplied by the projector on the state 0 plus projector on the state 1. So that's all for today. Thanks for your attention.